So, someone has a stroke and they can no longer speak. So that would be like, I don't know, in Broca's area, I always forget who's doing what there. But you could then put your chip, and your chip is maybe what the size of, I don't know, 10 millimeters or something like that.
Yeah, it's about 10 millimeters in diameter. And so it sits on the top of the brain, and then it has these tiny little hair-like electrodes. They're actually smaller than a human hair. They're made of platinum iridium, and then they insert down into the surface of the brain, and they record from neurons at a depth of about 1.5 millimeters.
Wow. So how do you get in there? I mean, this is brain surgery, right? You got to go cut through the skull and the whole thing. And then we're just saying, we'll just do this. I mean, that's like a major surgery.
It is. And also it's a safe surgery. So, I mean, it's not something you would trivialize, but people get surgeries like this when they have essential tremor or Parkinson's, and they receive what's called a deep brain stimulator. If you have epilepsy, you may have a piece of your skull removed, and you have electrodes placed on the surface of your brain to try to localize the center of the epilepsy to see if you'd be a candidate for surgery. These kinds of procedures are performed all the time, and as long as it's done in a safe way by a responsible neurosurgeon, the outcomes are really good.
And so when they close the brain back up, that doesn't change things forever. I mean, you don't have to keep taking anti-epileptic drugs or anything like that, seizure drugs, or?
No, I mean, you'll probably take an antibiotic and maybe some anti-inflammatories for the couple weeks after the surgery, but it's not something you have to be on continuous meds for.
Well, I only asked because my mom had 5 craniometries for a meningioma brain tumors.
Oh, yeah.
That ultimately killed her after about a decade. Yeah, it was a pretty big deal, but they're carving out huge portions of tumors and stuff. It was a pretty massive area.
I'm actually glad that you mentioned that, because sometimes people will cite these brain surgery statistics that actually pool data between these relatively innocuous procedures like a deep brain stimulator or epilepsy monitoring with major brain surgeries where you could even have like a lobectomy. And, it's important whenever I'm thinking about, the surgery that we're performing, I'm comparing it to the next closest major procedure, which is either DBS or epilepsy monitoring. But if you just go and you Google or you use ChatGPT or something like that and try to find statistics on intracranial surgeries, it's often pooling over cancer treatments and sort of like large epilepsy surgeries. So it's an important distinction for sure.
Yeah. Okay, so you got this tiny little 10 millimeter with the 400 something wires. How do you know which neurons or which neural network area or whatever module you're going to stick it there on the motor cortex? What if it's 10 millimeters to the right or left? It should have been. How do you know exactly where to go?
So there's anatomical organization which sort of maps, what areas of the body are controlled by what parts of motor cortex, and they're fairly well conserved. So by and large, a neurosurgeon just looking at the surface of the brain would know. For the early feasibility studies coming into this, because we want every single trial to have the most information possible, we're also doing functional imaging, where someone will get an fMRI beforehand, which is able to localize brain activity through medical imaging. So someone will attempt a task like speaking, and then you'll see what areas of the brain light up when they're speaking. And we can use that, and we can lay that over the anatomy and make sure that we're going into the exactly right location. Now, targeting in brain-computer interfaces, it's not a neuron-to-neuron target. It's really like a millimeter scale targeting to get in the right area. And then the decoding algorithm is akin to, okay, now we've dropped microphones into this crowded stadium, and now we need to figure out like which speakers who and how to map that activity onto the desired outcome. And so we never know a priori when we drop down which neurons we'll be listening to, but that's the job of the machine learning algorithm, is to provide that alignment.
Oh, wow. And so even if you're off a little bit, could the patient then learn to reprogram those neurons to do the job?
Yeah, for sure. And actually, there's a really interesting story about, this is not a person, but this is a monkey. It was at the University of Pittsburgh that was when they went to finally look and see like exactly where the device was, like for at the end of the study, they found that the surgeon had misplaced it, and instead of putting it in motor cortex, they put it in the somatosensory cortex. But even with the device located in the touch area of the brain instead of the motor area of the brain, the monkey still learned to volitionally control it and was performing at levels that was the same as all of his friends. And so the brain is remarkably plastic, and we're very good learners. And so even if things were placed in the totally wrong area of the brain, you could likely still use it. There's also work on, there was a patient that was treated at Stanford that received a device in the area of his brain that controls the hand. But in between sessions where they were doing hand-based decoding, they were talking to him, and they noticed that they're looking at the kind of neural activity on the screens, and when he's talking, the neurons are lighting up, and they actually figured out that they could decode speech from the hand area of the brain. It wasn't as good as if you go into the speech area of the brain, but even just the coupling between the hand and mouth areas, because we do so many things that require coordination, that coupling is so good that you can even do speech decoding in the hand area of the brain.
That's amazing. Wow. Could you do it while the patient is awake? I mean, you do the surgery, wake them up, and then go, okay, we're going to poke around here and here, and then see what the response is?
You could do it, and for certain brain surgeries, that's what they do. Before they cut anything out, they always want to make sure exactly what it does. But in these sorts of BCI recording surgeries, it's usually the case that they're anesthetized, and you already have enough fiducials and you know where you're going that you just place the device once.